while acceleration is the last major motion idea we're going to cover, I did say that there are a lot of ways you can approach it. All right, so we're going to deal with constant acceleration in one dimension, so up and down, back and forth. All right, there won't be anything at angles. But we are going to introduce how to relate not only acceleration to changes in velocity, but also how that affects distance. So, for all of our acceleration equations, all right, you want to be familiar and be able to recognize these variables, because these will be used over and over and over again in your equations. So v without a subscript is your final velocity. V with an O as a subscript is your initial velocity. X stands for position. XO, or with the subscript not at the beginning of it, is your initial position. A stands for acceleration. T stands for time. All right. Big ones to kind of remember is that the V naught or X naught, the little O thing, always means your initial, okay? And then X, just remember that's related to distance. So your kinematic equations or your uniform accelerated motion equations, all right, we'll kind of abbreviate them as UAMs, all right, are these guys. All right, so we've already dealt with the first one. All right, we have velocity equals your initial velocity plus the acceleration times time. And then these guys bring in distance. All right, so the total distance traveled is equal to your initial position, which oftentimes is 0, but every once in a while you might run into an equation that says, if you start at 10 meters, then where do you end at? All right, but your initial position plus your initial velocity times the time it takes plus 1/2 your acceleration times that time squared. Okay, so the only thing here that's squared is time. Another relationship, or kind of rearranging that equation or being able to get rid of t, is your final velocity squared is going to be equal to your initial velocity squared plus twice the acceleration times your change in position. Okay? So, you'll have plenty of practice using these, but just keep them in mind. Write this on a note card or print off the AP equation sheet and just have that handy as you're going through these, okay? So, to give you some UAM or kinematic practice, we have an airplane that accelerates down a runway at 3.2 meters per second for 32.8 seconds. How far does it go? Okay. So, these equations are sometimes where it comes in handy listing out your knowns. So we have accelerating down a runway, so our acceleration is 3.2 meters per second squared, and we know that the time it takes is 32.8 seconds, all right? Based on the information given to us, we're going to assume that our initial velocity is 0, all right? And because it doesn't tell us that we have an initial velocity, so that's the only assumption we can make, and we want to find distance. So, which of our equations involves all of these variables? So here's our L. Our equation is the x equals xo plus vot plus 1/2 at squared. All right, so we aren't given an initial position, so we're just going to make that 0, so we can get rid of that. We don't have an initial velocity, so if that is 0 and we multiply it by time, we get 0, so that part of the equation falls out. So we're just actually going to have x equals 1/2 at squared. So if we substitute in our knowns, we'll have 1/2 times 3.2 times 32.8 squared. And if we solve, let's plug that in the calculator, 0.5 times 3.2 times 32.8 squared, you end up getting 1,721.34 in our units because we're solving for x, be meters. Okay? The trickiest thing with any of these is just to make sure that you only square the one variable that's squared. Okay? The acceleration isn't squared, the 1/2 isn't squared, it's just the time. Alright, so another sample problem. It was once recorded that Jaguar left some skid marks 290 meters in length. Assuming that the Jaguar skidded to a stop with a constant acceleration of 3.9 meters per second, determine the velocity of the Jaguar before it began to skid. Okay, so again, these help when you list out what you know. We know that our distance is 290 meters. Okay, we know that assuming it skidded to a stop, so our final velocity is 0 meters per second. All right, we know that our acceleration is negative 3.9. And we know that we want to find our initial velocity. So which equation has all of that information in it? That's going to be our v squared equals VO squared plus 2a x minus xo. So again, kind of thinking about what we know, we're not given a initial position, so we're just going to assume that's 0, so that variable falls out. And then from there we plug things in. So we're really dealing with v squared equals VO squared plus 2ax. So we know that if we substitute in our knowns, we're going to put 0 in for v. VO is our unknown. Actually, this is a good time to practice rearranging equations, so I'm not going to plug it in this way. If we continue messing around with our equation, we'll have v squared minus 2ax equals VO squared. And then if we take square root of both sides, VO equals square root v squared minus 2ax. All right? So when we substitute, we're going to have the square root of 0 squared minus 2 times negative 3.9 times 290. Again, this actually helps you prevent mistakes rearranging here because you're going to be forced to recognize that you need that negative sign in there, all right, so that your numbers end up canceling out and you can actually take the square root, all right? So if you solve, you're going to have negative 2 times negative 3.9 times 290, and then adding 0 to that doesn't make a difference, so take the square root, and you'll have 33.6 meters per second. I already did the U for you. All right? So this is definitely something that you need to do a lot of practice with. Get through as many of the practice things as you can until you feel confident about choosing the equations, plugging things in the right place, and then you'll be ready for your quiz.